Either way is fine. It'll be an interesting day, when someone, makes a T-shirt, and on it it says, I survived tax classes. That would be kind of interesting, funny to some people and troubling to others. Nah, I think it's pretty easy. Okay, so we'll focus on this particular instruction, which is a subtraction instruction. I picked this instruction instead of the one on top of it because subtraction is not commutative. Okay, so we can confirm whether it works the way it's supposed to, a little bit more so than the addition instruction. So we look at this instruction and go like, okay, so tell me what these various columns are saying, okay? Because you need to know how to read this spreadsheet, okay? So column A is a bit pattern. The bit pattern is understood by the processor. Now, when I say understood, I put it in quotes, okay? But it can be interpreted by the processor, and then from the bit pattern of column A, the processor would know what to do. Is that okay? But this is natively what the processor can do, okay? The processor cannot read, what is on the second or the third column. Are we good so far? Okay. So when you look at column B, this is what we call the mnemonic of a particular opcode. Column A gives you all the opcodes, operation codes. Column B gives you all the mnemonics. And mnemonic is basically a name that is easier for us to remember, so that you don't have to deal with all zeros and ones all the time. Is that okay? So when you look at the mnemonic in column B, X refers to one of the four registers, A, B, C, or D. Y also refers to one of the four registers, A, B, C, or D. So in this case, the subtraction instruction can specify any one of the four registers as X and any one of the four registers as Y. Is that okay? Column C is the C explanation, or explaining the instruction, but using C code as a way to explain it. So in this case, it is the same thing as register X gets register X minus register Y. Is that okay? So some of the stuff on column C can be a little bit harder to explain, like these guys over here. We'll get to those later, okay? But today we'll start with something that's relatively simple. And then column D is just an English description of what the instruction does. So in this case, all it does is subtraction. So are we good so far with this explanation? Okay. You might also notice that there's another instruction that is kind of like subtract, but is not subtract. Let's see, is it even on screen at this point? It's not on screen at this point, but I'll scroll down so that you can see that one, because there's a very minor but significant difference between these two. Look at this one here. It's compare. So how does compare differ from subtract? Exactly. One does not store the result of the subtraction. So compare goes through exactly the same motion as subtraction, but it doesn't store the difference. The difference is computed and then it's tossed away. Then you ask, why? Well, because in the subtraction process, it will still change or potentially change the borrow flag. It will change the overflow flag, the sign flag, and also the L flag. So with those flags and combined with some conditional branch instructions, we'll be able to make decisions. Should I continue execution in a straight line, or should I branch and go somewhere else? Okay. So we'll talk about conditional branch instructions later, but I do want to emphasize that there are two instructions, both involving subtraction. One stores the result of the subtraction, and the other one does not. Are we good so far? Okay, all right. All right, so we're going to focus on the subtract instruction today. Now, if I want to subtract register, let's pick something different from your lab, okay? So let's say we want to subtract register A from register C. Okay, what bit pattern should we be are we going to look at? So let's go ahead and check it out. Okay, I'm just trying to find a. Okay, I'll just start a new one here. Mouse pad. There we go. Okay. So what we want to do is to say register C gets register C minus register A. This is what we want. So which one becomes register X? Register C, right? So X is register C, and then Y is register A. What bit pattern do we use to represent register C? It's just 1 0. It's just 1 0. We only need 2 bits to specify one of the 4 registers. So register C is just 1 0. Okay? So we'll say XX in this case is 1 0 in base 2. And then YY is just 0 0. Very good. All right. So knowing all of this stuff here, we know every single subtraction instruction starts with the fixed bit pattern of 1 0 0 1. So that means subtract CA has an opcode of 1001, and then we have 1000. Is that okay? But when we play with the Logisim, it doesn't use binary very often because that takes a lot of digits. So most of the time we want to convert it into hexadecimal. So when you convert 1001, 1000 into hexadecimal, well, I put that space in between, because it's the right place to separate the two 4-bit chunks. So 1001 is 9 in hexadecimal, and then 1000 is 8 in hexadecimal. So this opcode is 98 in hexadecimal. So how is 98 in hexadecimal different from 1001, 1000 in base 2? What do you think? There's no difference. It's just different names for the same thing. Is that okay? All right? Okay. So with this, we're almost done with just looking at this table. There's one more thing we have to look at. The other thing we have to look at is the halt instruction. So you look at the halt instruction, the opcode is pretty easy, right? This one is just all zeros except for the least significant bit, which is a 1. So in hexadecimal, it is just 0, 1. Okay, no problem. What does it do? The mnemonic is the actual word of halt, so it just says halt. What does that mean in English, halt? Stop, okay? Now, who on earth would use this word instead of stop? Police in Great Britain, to be more exact, right? You're waving the little club and go, halt, halt, and then trying to blow the whistle at the same time. That's a very stereotypical picture of a British cop trying to stop someone. Okay, what about the C notation? What is the C notation is telling you? Because that is what the instruction is going to do. What is this going to do in the C program and then just in the parentheses 2 semicolons and then a semicolon right after that? What does it do? It's a for loop, but it's a very interesting kind of for loop. What does it do? Nothing. Very good. And when do we get out? Never. Okay? This is a forever loop. This is an endless loop. Okay? So what does it mean when we have an instruction that corresponds to this infinite loop? It means halt in parentheses forever. We're not getting out. Okay? Once you execute the halt instruction, you cannot get out of it. Okay? Now, why do we need a halt instruction? Well, because we need to be able to stop the execution of a program when it is done. Then you might say, well, when we run out of space to run the program, then we'll stop. The answer is no, you cannot run out of space to run a program. Because when you get to location 255, the next instruction it will execute is at location 0. It wraps around. There's no natural end to where the program can execute. Is that okay? So that's why we need an instruction like this, so that we can specify when we get to this instruction, everything will stop. Okay? That makes it a whole lot easier for us to say, okay, at least we get to a point when the program stops, then we can go back and look at the registers, we can look at the memory content and see what happens and see whether the program performs correctly or not. Is that okay? So the halt instruction is really just saying, okay, it's kind of the same thing as return 0 in main, okay? It tells us, yep, this is the end of the whole thing, okay? So I think with this, we can now start to, we can go back to LogicSim. And I'm going to do a hard reset. Now, there are several ways to reset LogicSim when it comes to TTP. So when you go to the design at the top, there's a reset button here. Now, this reset button does reset. It is the same. This reset signal goes to every single component that has a clear reset or 0 pin. Okay, so that includes all the registers, but it does not include the RAM component. The RAM component has its own reset. So if I click this, okay, using a poking tool, if I click this, it will reset, all of the components except for RAM. And you can see that the RAM component here, has its own little reset. Has its own little reset button here. The reason why that is the case is because if you reset the RAM, it will also clear out the content of RAM. So if you're trying to debug a particular program, you may not want to do that. Because if you did, then you have to reload the program every single time you reset the processor. Yes?
The reset won't reset the ROM either, right?
That is correct. ROM as read-only memory retains its content across resets and power up and downs. Okay, very good. So in this case, I'm going to reset the ROM too, because I want to show you how to put content back into ROM. But there's still one thing not being reset. It has to do with the clock. Okay, so the clock, if it was high to begin with, it would not be reset by either of the reset buttons. That can only be reset by resetting the simulator itself. Okay, or you can just manually click the clock line so it goes back to low, and then you hit the reset buttons for the processor itself. Okay. Now, if things are not working right, you can always go back here and say reset simulation. Now, that will reset everything. Okay. If you go to the simulate menu and then you say reset simulator, it will reset everything, including the content of RAM. But that is also the most surefire way to reset everything to a known state. Okay, so if things are not working right, try to reset the entire simulation. If that is not working, get out of LogicSim, close, and then restart LogicSim, because sometimes LogicSim does get into a state when it doesn't work properly. Okay, so now that we have reset the whole thing, we'll go into the RAM component, go to Edit Content, and enter those 2 bytes. The first byte is, if I remember correctly, 98, right? 98 for the subtraction instruction. And then the second one is 01, which is the halt instruction. So now the program, so I can now close this window. So now there's a program in RAM. So before we go any further, I have to kind of steal one of the analogies that one of my students came up with yesterday. Since I'm not a sports fan, okay, these things never come to my mind by itself. But that person said RAM is kind of like a coach in a football game, and a ROM is a playbook. Okay. So does anyone want to help me explain what is a playbook in the context of football? Because we cannot assume everybody in class understands what is playbook. Go ahead.
Can we not assume that? I thought everybody does know that.
I don't know. I don't.
It's just like your textbook, right? It just has like instructions on how to do the thing.
I thought it was like the little chalkboard with the circle.
Yeah, exactly. And then like one circle goes to another circle. It's just like instructions on like how to do plays. Oh, really? Yeah.
See, that validates my assumption that not everybody knows about what a playbook is. Okay, so I'm gonna cheat here, and I'm gonna look for playbook.
I think it's soccer.
Soccer has no playbook. Soccer is just completely, everything is impromptu. It's like, which is part of the fun of that whole thing, right? Yep. And it doesn't have like, doesn't have pauses every 3 minutes. Every 3 minutes you have a break of like 2.
I didn't grow up here, so when I see football, I'm like, why do they stop all the time? Just play.
So apparently a playbook, according to Google, is a book containing a sports team strategies and plays, especially in football. Okay? So you can also look into pages within a playbook. Okay, pages in playbook. And then we'll look for images. And that's when you see all the squiggly lines and the squares and the crosses and whatnot. So we'll take a look at that.
It's just like stopping.
Okay.
Man, they have SEO'd hard.
Hmm?
They forced themselves to the
It's just LinkedIn.
front page. Yeah, that's what I'm saying.
There we go. This is a good one. So, it says what? Under China. Well, it's still a playbook, okay? It's still a playbook. But I don't understand why it's under China. Let's try this one. This one looks more interesting. Passing game site adjustment.
See the arrows in the circle.
Hmm?
The arrows in the circle.
Okay, so it is the chalkboard.
Yeah.
Okay, so this is what a playbook, a page from a playbook looks like. So the coach will be muttering some words into the mic, and then the quarterback, all the players will be receiving, instructions like, okay, trips, is it route 39? I don't know what RT stands for. Trips right. Okay. So trips right 39. So when all the players, hear this term, each player, okay, depending on which role they're playing, will know what to do. Hopefully. Okay? So the quarterback is the one who's screaming out, this term, or not screaming because they don't want the other team to know. But this term will be disclosed to all the players, and all the players in the field will know what to do based on their role. Is that okay? But the playbook by itself is not going to do anything. Okay? The playbook is only there to instruct the individual players what they should be doing. And the coach is the one who is choosing which play of the playbook to use for a particular, how do you call that in a football game? For a particular play, for the particular play. That's a good way to put it. Because football is play by play. Okay, it's kind of like a role-playing game. It's roll. Yeah, exactly. You have to, except for the dice rolling part. Whereas a soccer game is continuous. There's no break. A soccer game is more like a real video game where, can I stop and think about what weapon to use next? No. Okay, so that. I thought that was a pretty good analogy, because in the case of a processor, it is also play by play. Okay, except we don't say play, we say edge or clock. Okay, so it's clock by clock. So let's try to figure out what the processor is going to do when it executes this rather simple program. Now, before going even further, we're going to go into the register bank and put something into register A and register C, just so that we can see that it works or not. Okay? We are subtracting register A from register C. So I'm just going to put 1, 2 in hexadecimal into register C, and we'll put 6E into register A. Okay? So before we go any further, we should know what the answer is, right? So we're going to go through this subtraction and figure out what the answer is supposed to be. So we have 1, 2 in register C minus 6E in register A. So this time I'm going to do a base 16 subtraction. Okay, so we'll try to figure out what is 2 minus E. E is representing 14. Okay, so 2 is less than 14, which means we need to borrow. But when you borrow 1 from the more significant digit in base 16, you're borrowing a quantity of 16. So you end up with 18 minus 14, which is a 4. Is that okay?
Can you explain that again?
Sure. So 2 is less than E, so we need to borrow. When you borrow 1 from the digit to the left-hand side, you're borrowing 16. Because this is in base 16, so when you borrow, you're borrowing 16. So after you borrow 16, your 2 becomes 16 plus 2, which is 18, right? The quantity of 18. E is representing the quantity of 14. 18 minus 14 is 4. So that's why we got a 4 as a result, but we do have a borrow. So now it becomes 1 minus 6 minus 1 because we have a borrow. So essentially it is 0 minus 6. So once again, 0 is less than 6. We need to borrow. When you borrow, you're borrowing 16. So now we have 16 plus 0 as our minuend, and then we are subtracting 6 from it. 16 minus 6 has a result of 10, but we don't say 10 as 1, 0 in base 16. In base 16, we say it is A, okay? And we end up with an overall borrow of 1. Is that okay? So base 16 subtraction is no different from base 2 or base 10. It is just, the tricky part is when you borrow, how much are you borrowing? In base 10, you're borrowing 10. In base 2, you're borrowing 2. In base 16, you're borrowing 16. That's the real trick to doing subtraction in other bases. Yes?
Could you explain the steps during and after the 0 minus 6 part again?
Okay, so the 0 minus 6 is 0 is less than 6, so that means we need to borrow. So we are borrowing from a digit that doesn't exist, which is fine. Okay, so now we have when we borrow, every time we borrow, we are borrowing 16 because this is a base 16 number. So now we have 16 minus 6. Is that making any sense?
Okay, and it would still be 16. All right, so even if in the second digit, it would still be borrowing 16 from the third digit then? The third digit that does not exist?
Correct. So we have an overall borrow of 1, but in terms of actual quantity, we're actually borrowing from 16 times 16.
Okay.
Yep, so which is 256. So that means we are owing 256, but what we have in our pocket would be this amount, which is 164 in base 10. Do you know how I can tell this is 164 that fast? Because A is 10, right? And that digit is representing how many 16s we have. So we have 10 of the 16s, which is 160 in base 10. The 4 is 4, because it's the digit part of the entire number. So we have 100 plus 160 plus 4, and therefore 164. Okay. So anyway, we can double check and see if the processor is going to come to the same result, okay, which is the whole point of doing this by hand first. Okay, so now we have set up the register bank, and so it's time to start the execution of the program. So the question is, okay, let me zoom out so that we can kind of get a sense of how dreadful the situation is now what do we do? How do we track down the execution of an instruction? Okay, now you kind of have to pay attention here, or at least kind of jot down the time, which is 9:40-ish. Okay, because you will probably need to follow this process a few times with different instructions to understand how instructions execute in the processor. And by doing this, you are studying. Okay, there's no text to study for this portion of the class. Okay, studying is understanding the processor architecture and be able to follow the signals and follow the components and understand how one component affects other components. Okay, so this is how we study for this portion of the class. Is that okay? Yep.
When we have an exam, the one coming up,
Mm-hmm.
will we need to know how parts connect
Yes.
beyond generic, specifically in the toy processor?
you will need a full understanding of the toy processor, how the components interconnect and how they function as a whole unit.
Will one be provided, like a picture of it be provided for the, or should we?
No, but you'll be bringing yours. Now, you'll be bringing yours is actually a good thing because, okay, first of all, let me teach you guys how to do that, okay? How you can print and annotate your own picture, okay? It's not different, huh? We did it last time? Okay. So what you should do, okay, is to generate the bitmap first, okay? And then you put it into a document, and then you can, depending on what you use, you can annotate the various parts of that picture. Okay, so you can add your own color coding, you can do all kinds of annotation so that it is easier and quicker for you to find something in that picture. Is that okay? Yep.
When is the next exam, by the way?
It's around week 12. We are in week 9 right now, so we are still at least 2 weeks off from that. And hopefully I will have the previous exam graded by that time. I'm intending to do a lot of grading over this weekend, so I think we can get it, by next week. Okay. All right. So, getting back to this picture, okay? So now the question is, where do I start, right? I mean, this is like a big mess. Where do I start? Well, you start with components that are activated. Okay? So what do we mean by, a component is activated? If anything has a select, pay attention to the select. If anything has an enable, pay attention to the enable. Okay? If something has an enable but is turned off, then it may not be as important as another component that is enabled. Does that make sense? Okay? All right. So with that in mind, then we look at all the components. Now, there are several components are particularly important. Now, don't pay too much attention to the multiplexers and the demultiplexers, because the multiplexers and demultiplexers, like this guy, this guy, this guy, this big guy over here, this guy, and so on, and this guy over here, the multiplexers and demultiplexers are only there to switch the paths, okay? They are only a means to an end. As a result, don't pay too much attention initially to the switches. Pay attention to the things that can actually do something, okay? What do you mean when you say something, some components that can actually do something? Registers, okay? Because registers can retain the content of something. It can also change its content, right? So registers are important to track. 2, the ALU. This is the only part of the entire processor that performs any kind of computation, adding, subtracting, bit shifting, bitwise odd, bitwise not, bitwise and, bitwise or. Okay, so pay attention to the ALU. Pay attention to RAM, because RAM is where we get the instructions. It's also where we get data to process. It is also where we store processed data back into. So RAM is also very important. Okay. Now, if you filter out all the things that are not so important, the really important portions are actually not that much. Okay. You got 1, the RAM module over here. You get the ALU over here. The register bank is important. Okay. You have the program counter, which is a register here. You have the instruction register over here. You have the microcode pointer down here. And that's about it. Those are the active components that you have to focus on and go like, is this being used? Okay. So are we good? Are we okay so far in terms of how to start the analysis of what the processor is doing? Are we good? Okay. So in this particular time slice, okay, I call this a time slice because everything is static at this point. Okay. Things only change on transitions, okay, of rising edge or falling edge. But when we do not have edges, everything is static, okay, which is great because we can actually look at one single frame of time and go, well, we can analyze the frame of time, in details. So in this particular picture, okay, you can see that RAM is selected. How do we know? Because SEL, select of RAM, has a light green line attached to it. That means it is selected. Okay? So if RAM is selected, it should automatically have two additional questions, kind of like super automatic. The first question is, are we reading or writing? And then the second question is, which location of the RAM are we interested in? Does that make sense? Because that's the whole idea of RAM. RAM is just a place where we can store a whole bunch of bytes. Okay? But in order to either store or retrieve a byte, we have to tell the RAM component which location we want to retrieve. Does that make sense? Okay? So as soon as cell is green, we automatically ask two additional questions. Where is A attached to? Who is telling this particular RAM component which location we want to access? And two, are we reading or writing? Okay? Let's answer the easier question first, which is, are we reading or writing? That's the load pin. It is connected to RAM load, which is coming straight from the ROM, and it's saying 1. So are we reading or are we writing? We are reading. Very good. Okay, so we are reading. Okay, which location are we reading? Now, I know you can see that we are addressing location 0, 0, but what is telling the RAM component that location 0, 0 is where we should be reading? So what do? We track down the component that is specifying the address port in this case. I'm just double checking, making sure the battery is still good. Okay, so you can click on the wire, and it highlights the whole net of where it goes. So you can see that it goes into one output pin. The output pin is only here for debugging purposes. Okay, so it doesn't really serve any purpose other than, yeah, we see that the address bus or the address port has a content of all zeros. Then it goes into a multiplexer. Then what should we do? Okay, this is a multiplexer, which means it is selecting one of the inputs to become the output. So what do we do next? What do we look at next? The select pin, exactly. So we look at the select pin of the multiplexer. Graphically, where is the select pin? The one that is below the gray dot, okay? So it is a light green, which means it is 1, right? So which one of the inputs should I track next? Input 1, very good. So now we track this one down, and it goes to a register, as well as an adder. The adder is not an issue because we know whatever we are interested in has to be driving this particular wire and not sensing this particular wire. This is an input pin. It's not really useful to us in this discussion. This is an output pin. Q of PC is an output. So that is what is driving the address port eventually. Is that okay? The program counter, yes, go ahead.
Sorry, I'm a little lost. Why would you choose the output pin you want a multiplexer again?
Why would we choose input pin 1? Because select is 1. The select line is telling the multiplexer which input it should connect to the output. So that is why we are only interested in input 1, because input 0 is not selected. Okay? All right. So the program counter is exactly what the name implies. It is a program counter, which means it tells us which location contains the next opcode in memory to execute. That is the job of the program counter. Okay? So you might want to write this down, or you can watch the video again and write it down later. But the job of the program counter is to tell the processor where is the next location to get an opcode to process, to execute. Is that okay? Okay, so we have just answered a few questions about the RAM component. Yes, go ahead.
So aside from program counter, which you just told us, is there a document that has the full names of all these things?
There is not as of yet.
Will there be?
I can work on one. Or you can work on one and I can publish it. Yes.
Did you repeat the program counter?
Hmm?
Did you repeat what you said about the program counter?
The program counter, tells the processor which location in RAM is the opcode to execute. Yep.
So I'm just trying to figure out how to study for the exam.
Mm-hmm.
You said that you need to know all this, and you said you're not going to have a picture. So how are we? Are you going to ask us?
But it's open book and open notes. You can print your own pictures.
I mean, but we can't highlight wires. So.
You can do that yes, you can. Okay, there are several ways to do this. Now, if you want to, take a picture, where things are highlighted in different colors and whatnot, this is what I would do. Okay, you zoom out, make sure that the portion that you're interested in is in the picture. Okay, so let's say this is all I need to capture. Okay, you go to your snipping tool in Windows, which I do not have, but I do have a screenshot tool. Okay, and you say select a region. So now you have a bitmap that is color coded. Do whatever you want with it then, right? Yep. Okay. So we just answered 3 questions about the RAM. Is it active? Yes. Are we reading or writing? We are reading. Who is telling us where to read in RAM? The program counter. Okay? So the 4th question, which is the last question we should ask when RAM is active, is where is it going? Where is the data of that location going? Does that make sense that should be one of the questions? Okay, since we are reading, why are we reading it? Okay, so to answer that question, we are going to RAM again, and this time we look at the data port. We try to track down the data port and see who is paying attention to the data port. Now, the moment you click on the data port, you can see 98 or 1001, 1000 is already on that wire, which makes sense, right? It is already reading that location. The question is, why are we reading this location? Who is getting changed as a result of reading this location? So you follow this wire, okay? It is a lot more cumbersome when I'm doing this on the projector than when you are doing it on your screen, because you have better resolution, right? A bigger screen than what you're seeing here. So you don't have to scroll and pan, and zoom in and zoom out to get this done. Okay, it goes into this demultiplexer. Do you think I should be concerned about this particular connection, that this particular demultiplexer connects to this wire? Nope. And why not? Because it's an output, right? And as an output, it should be off because you don't want 2 things to be outputting to the same wire at the same time. And we know this demultiplexer is not driving because this line here, which is the enable of this particular demultiplexer, is off. So this particular demultiplexer is off. None of the output is driving. So it is of no concern to us. Okay, where else is it going? This is an output pin, which is only for debugging purposes, so we can actually visualize what data is on that wire. And it goes around to here. Should we be concerned about this one? Well, we should not be concerned about this one because even though this is an input pin, the input pin goes, okay, first of all, the select of this particular multiplexer is a 0. So that means nobody is paying attention. As far as this multiplexer is concerned, it is not paying attention to the wire that we have selected. So that is not a concern for us either. Okay, let's see where else it is going. So we go down here. It's also going to this instruction register. Is that significant? Yes, it is. Why is that significant? Because it is enabled. Okay? So the instruction register is enabled. Then you go like, well, if it is enabled, how come it's not getting the content of 98? Because it's waiting for a rising edge. Very good. Okay. So the moment I type Control T, which transitions the clock to the other state, the instruction register will become 98. Okay. So let's do a Control T to single clock. Okay. So now the clock line is high, okay? So you would say, okay, most of the components only respond when the clock has a rising edge, except for one component. Everybody except for one component responds to a falling edge. The one thing or the one component that responds to a falling edge is the microcode pointer. Okay, we call this the microcode pointer. Okay, so before we see how it is going to change, with the falling edge, let's see how it's hooked up. Okay, so we'll go ahead and analyze a few wires. So the first thing is it going to be updated? Is it enabled? Yes, it is always enabled, okay, because the enable line is connected to 1, so that means it is always enabled. Yes?
What is the 99A going to do?
It's not going to do anything for this falling edge, but the next rising edge it will do something. So we'll look at that when it is time to look at it, okay? So okay, first getting back to the microcode pointer, it's always enabled. It's always going to update on a falling edge. Okay. Next question. How is it going to update? Well, first of all, what is the output going to be used for? Well, that's pretty simple. That's pretty simple because the Q port of the microcode pointer connects to the A port of ROM. What is that telling you? It's telling us which location of ROM we should be looking at. Yes? Okay. So the next question is go back here and say, how are we updating it? Well, it's going into a multiplexer. So every time you look at a multiplexer or a demultiplexer that is enabled, you have to ask the question, what is the select line, right? So in this case, the select line is a 1 at this point. So that means we are ignoring input 0, but we are taking input 1. Input 1, if you track it down, comes from the adder. And this adder is always just adding 1 because the carry is just a constant of 1, and then the other number is a constant of 0. So it's always just adding 1. So that means on the falling edge, what's going to happen to the microcode pointer? It's just going to increment. That's it. Okay? So it would just go to the next location. So the next location is 0D80004 in hexadecimal. So I'm going to give it another Control T on the keyboard. There we go. And you can see that, yep, the microcode pointer is now 001. And the ROM content is, the location of ROM has the content of 0D80004, which means the output, the data port of the ROM is going to have all of those bits spewed out. Is that okay? So now we have to go through that whole process again. Find out who is selected, who is enabled, and what the next clock edge is going to do. Is that okay? All right, so let's check it out. Let's find out what's going to happen. So the same thing, we go to RAM, because every time we use RAM, we answer a whole bunch of questions. But this time, RAM is not selected. So the other 3 questions that we're supposed to ask, we don't ask those anymore, okay? Because RAM is not paying attention. It is as if it is not there at this point, okay? So if RAM is not selected, let's go through the other stuff and find out what else is selected. The ALU is also not active because the enable line of the ALU is a 0. Okay, so nothing is happening to the ALU. We look at the register bank. In enable is also dark green, which means we are not updating any particular register. Okay. We look at register output 0 enable. It's dark green. We are not using output 0 of the register bank. Register output 1, is also not being used because the demultiplexer of register output 1 is also dark green, which means we are not using register output 1. So the entire register bank is not being in use at this point. We look at the program counter. The program counter has the enable being 1. So that means we now have to ask a few questions. Okay? How is the program counter going to be updated? That is the question. So for that, you have to analyze what is connecting to the D port of the program counter. This is coming from a multiplexer. The multiplexer select is dark green, which means it is selecting input 0. So we track down input 0. Input 0 is coming out of an adder. But this adder does not always add 1. Sometimes it can add 0. But in this case, it is adding 1 because the carry in or K0 into the adder is a 1 because address mux, ADDR mux is a 1. Okay, and this is an OR, so if at least one side is a 1, the whole thing is a 1. Are we good so far with this? So on the rising edge, how is the program counter going to update? It becomes a 1. Okay, it goes from 0 to 1. And the reason why the program counter, so this part you might want to write down, is why the program counter is incrementing. Because we have already grabbed the content of location 00 and put it into the instruction register. The program counter is now auto-incrementing to the next location. So we are ready for the execution of the next instruction. Is that making any sense? Is that okay? So getting back to what you were asking earlier is, so what are we doing with the instruction register? Okay, so let's try to answer that question. So for this particular clock, if I control T right now, the program counter is the only thing getting changed. Okay, it is going to increment from 00 to 01 because we're getting ready for the next opcode. So control T, and you can see the program counter increments to 1. But on the falling edge, we have something that is much more interesting to happen this time. Because on the falling edge, we already know that no register nor RAM is going to update on the falling edge except for the microcode pointer, which always gets updated on the falling edge, right? Because it's always enabled. But the question is, how is it getting? How is the microcode pointer getting updated on this particular falling edge? To analyze that, we say, well, let's check out what connects to the data port of the microcode pointer. It is coming from a multiplexer. The multiplexer has the select line being a dark green, which means it's selecting input 0, which is this particular wire. This wire looks like what we retrieved earlier, which is 9.8, but it's not just 9.8, it is 9.80. Why is that the case? It's because of the splitter. We have a splitter here that does something that's kind of funky. So the splitter says, okay, tunnel, which is really just the output of the instruction register, would give me bit 4 to bit 11. Okay? Then what about the least significant 4 bits? Bit 0 and 3 are coming from a constant of 0. Is that making sense? Okay? So it is as if we are shifting the output of the instruction register by 4 to the left-hand side. Yes?
Why is 9.8 bit 4 to bit 11?
Because we want to, how should I put it? Because I want to go to location 980 in ROM and not location 98. So for now, just kind of accept the fact that I want to go to a location that is a product of the opcode and some number. Okay? We are looking up a table. Is that okay? All right. So are we okay now in terms of understanding why on the falling edge right now the microcode pointer is going to update to 980? Are we done with that particular analysis? Are there any questions regarding that? Okay, I cannot differentiate between no question from I don't know what to ask, from I'm afraid to ask. You don't know what to ask. Okay, so there are questions. So, okay, so in that case, okay, so I'm trying to analyze the thought pattern, okay? So which part of this process, which part of the conclusion that the microcode pointer is going to update to 980 is not connecting in your mind. The concepts are not connecting.
At that point in ROM specifically,
We don't care what is in ROM. At this point, we're not concerned about what is in ROM. We're only concerned about microcode pointer and how it is going to how it will be updated.
But then why did you add the 0?
We'll see later. It has to do with the format of the playbook. Okay? But we'll explain that when we get to 980. The question now is, why are we flipping to page 980 on the playbook? Is that okay? I think I get your question, but it will be answered after we do a Control T. But so besides why we're going to location 980, are there any questions about why the microcode pointer is going to update to 980? I'll take it as a no. All right, so we're going to have a Control T. And after the Control T, okay, you can see that the microcode pointer is now at 980. So this is location 980. So with this picture, you cannot really quite see the reason why we put that extra 0 in hexadecimal into the microcode pointer. But once you look at the content, it'll be more clear. So if you look at the content at 980, which is this location, each location here is called a slice, or it's called a microcode, a step of microcode. Okay, so this is it's exercising all the control pins to the multiplexers, the enable, the select of all the components. So this gives me 16 steps that I can perform using a particular opcode. Remember what we said about the RAM is the coach and ROM is the playbook? Yes? Okay. So for each play, there are up to 16 individual steps. That is why we go to location 980, because the play is 98. Okay? The coach is calling out 98. Okay? And then what, right? What is play 98? Play 98 in this case is really simple. It only consists of one step. But if you have a complex play, okay, it might involve a few steps. So this gives me the room to have up to 16 steps per play. Does it mean every play is going to take up 16 steps? No. In fact, all of the plays that I have worked up at this point only takes one step. So I totally overestimated how many steps I need per play or per opcode. Is that okay? So does that answer your question? Why we are going to location 980? So I could have used a much smaller table because the instructions are actually very easy to implement. But it gives me the room to do something more complex later on if I wanted to. Yes?
So are you saying then that address 98, there's the possibility that there couldn't be room for all 16 steps?
I have only used up one of the 16 steps.
Right. Could you not at address 98?
98, not 98. They are different.
All right, well, could you not at address 98 then?
Huh?
Could you not at address 98 then? Possible.
Well, the location 980 is directly derived from the opcode itself. Okay, so if the coach says 98, and then all the players go like, I cannot remember play 98. What is that? So each of the players is now going to pull out a little playbook, right? Okay, I do have the right prop. Just give me a second. So each of the player, okay, it's not that pocket. It's this pocket. Okay, there we go. So each player saying, I did not study. I partied a little bit too much before the football game. Okay, but the coach is saying 98. What am I going to do? Look up page 98, right? All right, 98. Okay, so on page 98, there are 16 lines. Okay, where each line is telling each player what to do. So each play can have up to 16 steps. Now, this particular football team has very simplistic plays. So every single play actually only uses up one line on that page. But the page size itself has 16 lines. So if later on, if the coach wants to add a new play that is more complex, they can use up a page and go like, well, we'll fill in more of those steps. Yes?
The question is, so what is the purpose of adding the 980? If
Adding that 0, right? I totally overestimated how many steps I needed.
arbitrary?
It is somewhat arbitrary.
Got it.
I was thinking, 16 steps should be enough for anything I wanted to do. And that's why I picked 16. It should be a multiple of 4 because, I don't want to use a multiplier. Multipliers are expensive to implement. So if it is a multiple of 4, any multiplication of a power of 2 is just shifting. So we are just adding zeros to the right-hand side, which I can do easily with a merger.
So the 0 was just to make sure that there was
Plenty of space.
plenty of space.
Yes.
Okay.
Yep.
So an instruction would ideally be 4, 8, 16, 32 long, something like that.
That would be the number of steps I want to give myself. So as it turns out, 2 steps would be enough for all the instructions that I have implemented up to this point. But I'm leaving myself a lot more room, so if I wanted to, I can do something a lot more complex. Yep.
And say you do run out of space, could the last instruction be to go to the next memory location?
Well, that's a good question. If I do run out of space of the 16, I'm going to cannibalize the next opcode because the microcode pointer does not know what is the boundary of a page, so it will just keep incrementing. So I can actually have like in a particular play that would take up like 31 steps, but then I would just chew up the space of the following opcode because that opcode would land right in the middle of a play that belonged to a previous opcode. So I could implement something a lot longer, but then I will have fewer opcodes available in that case. So are we good so far with this analysis? This is a good discussion. Okay, so if you're missing some parts of this discussion or not fully understanding, a particular part of this conversation, make sure you kind of watch the video again, and listen, and also, try to jot down some notes. Yep.
So we've been talking a lot about ROM.
Mm-hmm.
And I guess my question is that when you're designing like computer systems and whatnot, does ROM have to be like built in the factory that way, or?
That is a good question, but given the amount of time we have left, let me finish this operation first, and then if we have time at the end of the lecture or in the lab, I can explain that part. Okay. All right. So you might want to jot that down because otherwise you might forget too, because I know I will forget. Okay. So what do we do at this point? Do the whole analysis again, right? See what is enabled and what is selected. The RAM component is not selected. Oof, okay, that means we don't have to ask the other 3 questions. And we look at the ALU. Okay, so the ALU says, the ALU is selected. Now, if the ALU is selected, you have to ask at least 2, if not 3 questions. Okay, the 2 questions have to do with 3 questions first, and then maybe 1 optional question after that. The 3 mandatory questions you should ask is, who is providing in 1, who's providing in 2, and what operation are we performing? So those are the questions that you automatically ask when you see the ALU is enabled. Okay? So we'll answer the easy question first. What operation are we specifying? So you click on the cell line or the select line, and the operation select is 0, 0, 1. We go like, but I don't remember what is 0, 0, 1. It's okay, not a problem. We go into the ALU, okay, which is its own little subcircuit, and we look at op cell, which is select, and when it is 0, 0, 1, that means we are subtracting. Because op cell is the select going to all the demultiplexers as well as the multiplexers. So we are sending the input pins to the second operation of the ALU, which turns out to be our subtractor. Are we good so far? Okay. All right, so now we know it is a subtraction that we are specifying. The next two questions would be, what are we subtracting? Let's track down in1 first, okay? So where is in1 coming from? It's coming from a demultiplexer. Should we pay attention to this demultiplexer? Yes, because it is enabled. What is this particular output being selected? Let's double check. You cannot visually see it, you have to click the wire. And it is, okay? So that means we should pay attention to the input of this particular demultiplexer, and it is coming out of output 0 of the register bank. Then the question is, which register in the register bank is connected to output 0 of the register bank? That is controlled by register output 0 select. So you click on this wire here, and it says 2. Which register corresponds to 2? Register C. Does that match what we were specifying? Okay? So that answers one of the two questions. The second question is, what about in2? What is providing in2? It is coming from this particular multiplexer. This multiplexer is really simple. One end, or input 1, is just the constant of 1, and input 0 connects to this demultiplexer. Based on the color of the wire going into the select pin, which one should I pay attention to? Input 0 or input 1? Input 0. Input 0 is this one, and it is coming out of another demultiplexer. And this demultiplexer is always enabled because you don't see an enable line. And output 1 is in fact the correct output because the select is 1. So now we should pay attention to the input of the demultiplexer. It is coming out of out 1 of the register bank. So the next question is, which register, A, B, C, or D, connects to output 1 of the register bank? So you have to click on this wire here. If it is, yep, there we go. It's 0, 0. Which register corresponds to the bit 0, 0? Register A. So we are sending register C and register A to the ALU, and the ALU is going to do a subtraction. Does that make sense to you? I think that's what we specified earlier, right? But wait, are we going to store the result of the calculation? So to answer that question, which is the fourth question when after you know the ALU is selected, is to follow the path of the output of the ALU. This one is fairly simple. It doesn't go to too many places. It goes into this multiplexer. So with this multiplexer, you have to ask two questions. Is it enabled? Yes. And which input connects to the output? 1. Okay, so we should track down the output now. And the output goes to IN, excuse me, I take it back. It goes to IN, or the input, register input. That is where we specify the content that we want to use to update a register. Okay, but which register is getting updated? Is any register going to be updated? Input enable is a 1. That tells us that at one register is going to be updated. Which register is getting updated? RISEL, register input select, is, okay, come on, it won't let me click on it. But it is, it should be 1, 0, okay? We can find out from going into the register bank here, and you can see that register input select is in fact 1, 0, which is register C. So register C is going to store register C minus register A, which is exactly what the subtract instruction was supposed to do. Is that okay? So everything is already set up. In fact, if you look at the register input, the wire, it is already the correct result, which is A4. Remember how we calculated A4? Yes? Okay. So we know on the rising edge, register C is going to be updated from 1, 2 to A4. So now we have a control T, and you can see register C is now updated. So zooming back out again, because a falling edge only affects the microcode pointer. So this is the part where it looks kind of mysterious, okay? So let's right click on edit content and go to location 980. So you can see the next location has a content of 2 followed by 6 zeros in hexadecimal, okay? So you would expect that this is what we see when we do a falling edge. Because when we do a falling edge, okay, if you look at the input of the microcode pointer, it is selecting input 1, which is coming from the adder, so we should be auto-incrementing, right? So are we ready for the control T? Are you guys ready for the surprise? Okay, it's a cliffhanger because we are almost running out of time. So until next Tuesday, we won't. You guys can find out on your own why that is the case. But when we do a control T, bam, it's not going to location 981. It's going straight back to location 000. Okay, so for the cliffhanger, I'm going to say a few things so that you can kind of try to process it and think about it. We are done with executing the subtraction instruction because the purpose of the whole instruction is to store the difference between register C and A in register C. We have accomplished that, right? So when you're done with one instruction, what are you supposed to do?
Halt.
Not yet. We have to get the halt instruction first. So we're going back to ROM location 000 because what does that do? It does what we call a fetch cycle. It gets the next opcode to execute. Okay? Location 001 is what we know as the decode cycle. It looks at the opcode that we just got and say, okay, what does it do? Okay, which page of the playbook should I turn to? That's location 001. Location 000 is kind of like turning on the headset to listen to the coach and say, what is the play again? Okay, that's location 000. It's called the fetch cycle. Location 001, on the other hand, is called the decode cycle, which is basically saying, yes, I heard you, coach, 98. Get the playbook out, flip to page 98. Okay, that is location 001. Once you get to page 98, the actual following of that play is specific to the instruction, so I cannot give you a generic description of that part. Okay, but at the end of every single play, there's one little thing that says, go back to page 000. Listen to the coach again. Does that make sense? So here we are, listening to the coach again. So this time, when you go through this entire cycle, we'll get to location 010 eventually. So I'm just going to fast forward to that part. And location 010 has all zeros. In other words, everything is turned off. Okay? Not only everything is turned off, but this microcode pointer cannot be turned off. Remember, that enable is always on, right? So that means it's going to get updated. But how is it going to get updated? This dark wire here, the dark green wire, is saying the multiplexer is taking from input 0. Input 0 is based on the instruction, so it will basically go back to the same thing over and over again. It's kind of like, the playbook instructions says, go back to the same page. Go back to the same page. Follow the first instruction on the playbook. On that page, it says, go back to the same page. So that's why it is an infinite loop. It cannot get out of that. So if I type Control T repeatedly at this point, you can see the clock is blinking, but nothing changes because every single component of the processor is turned off. So this concludes the little demonstration that I want to do, but this is how we're going to study for like the next week or so, is we look at different instructions and we follow the same process. Okay, there are some instructions that will work with memory, getting something from memory into a register. There will be some instructions to get the register content into memory. There will be some instructions for branching or jumping, like going to a different location to execute. So we'll look into all of those, but using the same method. Okay, so the way to study for this class is before I talk about the new instruction, you do it ahead of me. Do the same exercise and try to figure out what is going on in the processor that accomplishes what the instruction says it would accomplish. That would be the best way to study for the next few weeks. All right. No new lab today, okay? It's just the lab that we started on Tuesday. So if you're done with that one, there's nothing new to do. So I will see you guys next Tuesday. Have a nice weekend.